The number of elements that can exist in liquid state at room temperature, 25 degrees Celsius, and atmospheric pressure is. So under this standard temperature and pressure, there are two elements that can exist as liquids, bromine and mercury. Bromine exists as Br2 and mercury exists as liquid metal. If the temperature was raised to 30 degrees Celsius, there are three more elements that will exist as liquids. These are cesium, francium, and gallium. Therefore, the answer is 2. The second question. The correct increasing order of atomic radii of carbon, oxygen, aluminium, phosphorus, and calcium is. Along the period, the atomic radius decreases as the number of electrons in the outermost energy level increases. This causes a higher attraction between the electrons of the last energy level and the protons in the nucleus of the atom. Therefore, carbon being in the fourth group has a larger radius than oxygen being in the sixth group, as they both are in the second period. By this same reasoning, aluminium being in the third group is larger than phosphorus in the fifth group, as they are in the third period. Down the periodic table, as a new energy level is added, the atomic radius increases. Therefore, calcium has the highest atomic radius as it is in the fourth period. And then we have the atoms in the third period and the second periods. Therefore, the order is oxygen, carbon, phosphorus, aluminium, and calcium. So the answer is 2. Third question. What is the IUPAC name of the following compound? This compound has a triple bond, a ketone group, a methyl group, and a hydroxy group. First, we have to select the carbon chain having the maximum number of carbon atoms. There are two possible chains containing 5 carbons each. This chain and this chain. Because it has 5 carbons in the carbon chain, it will receive the name pent. We then select the carbon chain having the hydroxy group, as that has a higher priority than the methyl group. So we'll be selecting this chain. Out of the groups present, the ketone group has the highest priority according to the priority list. Therefore, the compound name must end with the suffix ONE, and the smallest carbon number should be given to the carbonyl carbon. As numbering from both directions gives the carbonyl carbon the number 3, we look at the next criteria. Double bonds and triple bonds, if present, should be given the smaller number. Therefore, we start numbering from here. And we number it 1, 2, 3, 4, and 5. Now we name the groups according to the alphabetical order along with the carbon they are attached to. So the IUPAC name will be 5-hydroxy, 4-methyl, pent, 1-ine, 3-on. So the answer will be number 4. The fourth question. Which of the following statement is not true with regard to elements in the second period from lithium to fluorine? The first statement. The highest negative electron affinity is shown by fluorine. Fluorine is the most electronegative element. Electrons can get tightly bound from outside, releasing a lot of energy. Therefore, this is correct. Second statement. The highest positive electron affinity is shown by beryllium. The first electron affinity is exothermic except in groups 2, 8, and in nitrogen. The second electron affinity is always endothermic. In the second period, neon is greater than beryllium, which is greater than nitrogen, with regard to their first electron affinity. But in the question, neon is not included. Therefore, beryllium can be considered as having the highest positive electron affinity here. Therefore, this is true. Third statement. The highest oxidation state is exhibited by carbon. The highest oxidation state exhibited by carbon is +4, example in carbon dioxide, whereas nitrogen can show +5 as in nitric acid. Therefore, this statement is false and is the answer. Fourth statement. The atomic radii decrease from lithium to fluorine. This is explained in question number 2. And number 5. The ability to form cations and to act as reducing agents decreases from lithium to fluorine. Lithium can form cations, whereas fluorine cannot. So this part of the statement is true. To act as reducing agents, the element should release electrons, that is, they should get oxidized. As fluorine is the most electronegative element, it cannot get oxidized, and this part of the statement is true as well. Therefore, the answer is 3. The identity of an electron in an atom can be expressed using 4 quantum numbers: n, l, ml, and ms. Identify which set of numbers given below is not acceptable as a set of quantum numbers for an electron in an atom. We'll take an example, 2s2. Here, 2 is n, which is the principal quantum number representing the main energy level. L is the azimuthal quantum number, which ranges from 0 to n-1 and represents the sub-energy level. 0 representing S, 1 representing P, and 2 representing D, and so on. ML is the magnetic quantum number and denotes the number of the orbital present in a specific sub-energy level, and these numbers range from -L to +L. So for example, if we consider the orbital S, it will be 0. If we consider the orbital P, it will be -1, 0, +1. And if we consider the orbital D, it will be -2, -1, 0, +1, and +2. Ms is the spin quantum number. 2 electrons occupy one orbital, and according to Pauli's exclusion principle, they have opposing spins, which is denoted by +½ and -½. So they are arranged in opposite directions. Now we'll take a look at the given answers. In 1, the orbital represented is the 0th orbital of the 4d energy level, which means it is possible. In number 2, the -1 orbital of the 3p energy level. In number 3, the -3 orbital cannot exist as the orbitals range from -L to +L, which in this case is from -2 to +2, and therefore this is not acceptable and is the answer. Taking a look at number 4, +1 orbital of 2p energy level, and in number 5, 0 orbital of the 4s energy level. Now we'll look at the 6th question. Which row of the following table gives the correct information with regard to the NSF molecule? We'll draw the structure of NSF. The oxidation state of sulfur here is +1, +2, +3, +4. Therefore, it is +4. There is no charge present on the sulfur atom, so the charge is 0. As there are 1, 2, 3 repulsion units present around the central sulfur atom, the hybridization is sp2 and the electron geometry is trigonal planar. Due to the lone pair, the repulsion exerted on the other two bond pairs is higher than what a bond pair would exert. Therefore, the NSF bond angle will be less than 120 degrees, but it will be greater than 90. The SF bond formed here is a sigma bond, therefore it involves the hybrid sp2 orbital of the sulfur atom and the 2p atomic orbital of the fluorine atom. So the answer matching all these criteria is answer number 5. Question number 7. A gaseous hydride of nitrogen NaHB was burnt in excess oxygen to give 10 cubic centimeters of nitrogen and 30 cubic centimeters of water vapor. The formula of the gaseous hydride is: as all of these exist as gases, we can assume that their volume is directly proportional to their amount. So we have 20 cubic centimeters of NaHB, 10 cubic centimeters of nitrogen, and 30 cubic centimeters of water vapor. If we simplify this, we get 2:1:3. So 2 NaHB plus O2 gives us N2 plus 3 water. As the sole source of nitrogen is NaHB, we have 2 nitrogen atoms on the right hand side, so we should have 2 on the left hand side. So here A will be equal to 1, as there are 2 NaHBs. And the sole source of hydrogen on the right hand side is water, and on the left hand side is this hydride. So we have 6 hydrogen atoms on the right hand side, therefore we should have 6 on the left hand side. So we have 2 of this hydride, so B will be 6 divided by 2, which is 3. So A equals 1, B equals 3. NH3 is the answer. So the answer is 1. Question number 8. Thermal decomposition of 15.6 grams of a hydrated metal carbonate, MCO3.4H2O, produces 4 grams of the metal oxide. The relative atomic mass of the metal M is. As the compound is given as MCO3 and the valency of carbonate is 2, we can assume that the valency of M is 2 as well. Therefore, the formula of the oxide formed by M will be MO, as the number of M atoms don't change. The moles of MCO2.4H2O is equal to the moles of MO. Therefore, 15.6 grams divided by the molecular mass of M plus 12 plus 16 into 3 plus 4 into 18 will be equal to 4.0 grams divided by M plus 16. This can be simplified as 15.6 divided by M plus 132 equal to 4 over M plus 16. Solving this gives M equals 24 grams per mole. Therefore, the answer is 5. Ninth question. Choose the molecule that does not have a dipole moment. SF2 has an angular shape derived from tetrahedral, so their dipole moments do not cancel out. PCl4 has a trigonal bipyramidal shape, which is a primary shape and would usually have a 0 dipole moment, but in this case the terminals are not all equal. Therefore, they do not cancel out. SF4 is a seesaw-shaped compound derived from trigonal bipyramidal. Again, the dipole moments do not cancel out. PCl3 is a pyramidal-shaped compound derived from tetrahedral, and the dipole moment is present. SF6, on the other hand, is an octahedral compound with a primary shape and has equal terminals. This compound is very stable due to its shape and as the F atom is very small, the SF bond is very short, contributing towards its stability. Even though an individual SF bond is polar, they cancel out, giving a compound with zero dipole moment. Therefore, the answer is 5. Question number 10. A solution has been prepared by mixing 250 cubic centimeters of a sodium sulfate solution of concentration 0.15 moles per cubic decimeter and 750 cubic centimeters of a sodium chloride solution of concentration 0.1 moles per cubic decimeter. The composition of this solution in terms of ppm sodium is. So first we have to find the total amount of sodium present. So we have to add the number of moles of sodium present in sodium sulfate and sodium chloride. To find the number of moles in sodium sulfate is N equals Cv. So we have the concentration given as 0.15 into volume given as 250 cubic centimeters divided by 1000 to make it into cubic decimeters, multiplied by 2, as we have 2 sodium atoms. Similarly, for sodium chloride, we have the concentration as 0.1 multiplied by 750 cubic centimeters divided by 1000 to convert it into decimeters. And here we multiplied by 1, as sodium chloride has only 1 sodium atom. So the total number of sodium moles will be 0.15 moles. ppm can also be represented by milligrams per cubic decimeter. Now we have to convert the moles of sodium into mass. So we enter 0.15 moles here, multiplied by 23 into 10 to the power 3 milligrams per mole, which is the molar mass of sodium, divided by the total volume, which is 250 cubic centimeters plus 750 cubic centimeters, giving exactly 1 cubic decimeter. Simplifying this will give us 3,450 milligrams per cubic decimeter, which is equal to 3,450 ppm. Therefore, the answer is 1.
Hey guys, if you liked our videos, please like, subscribe and turn on notifications. Thank you.